typically, there are quick ways to figure out. Is there sodium? Do you know a quick way to figure out if there's sodium in tap water?
Add a bit of chloride to see if it forms NaCl.
Actually, NaCl.
Or would NaCl form HCl?
No, NaCl won't precipitate out with the chloride. No. So what you do is you evaporate all the water. When you evaporate all the water, you're left with a solid residue at the bottom. But that solid residue is a mixture of different salts in there, and so it's hard. So you might look at the crystals and see, does that crystal look like a sodium chloride crystal? Are there other crystals that look like sodium chloride crystals? But there are other ways. One of the quick ways we do it is we just dip a piece of platinum or some other relatively inert metal, even stainless steel could work, and then put it in the flame. Do you know what color sodium ions give to the flame or impart to the flame? This is something I was watching TV, and I was flipping through the channels, and I saw some guy doing flame tests, and then I stopped. And I thought, wow, that's interesting. Not red. Sodium gives yellow, bright yellow. So we could tell. But the problem is everything you touch, you leave sodium ions. Did you know that? I used to work in sodium chemistry, and trying to detect small, minute amounts of sodium ion. And I couldn't use glass because, normal glass, it leaches out a little bit of sodium ion out of there. I had to use plastic containers. And I had to be careful. I couldn't touch anything because everything you touch, you leave a residue of sodium ions. And so it was very easy to cross-contaminate it. So it was quite a pain to do that. I was glad when I stopped doing that. Too much work. There are ways we can detect what's in there. It's not terribly difficult to figure out what the species are, but not with the equipment we have and other things. We aren't going to get into it, so we're just going to call it dissolved salts and leave it at that. The major species. What are the minor species? Did it ask you for the minor species? Yeah, so some people feel very uncomfortable leaving that blank, right? And so this is why just don't even bother with filling out the report sheet. We're going to do it differently. Okay. So I got that question as well. What are the minor species in tap water? Well, I'm sure there are going to be minor species and major species. Okay, then we have, number 11 would be C12H22O11. C12H22O11. Look at the ratio. What's the ratio between hydrogen and carbon?
Did we go over number 9 again?
I thought so. Ethanol. Did we do ethanol and ethanol aqueous? No? Okay, then I need to do that. This is actually pure ethanol. 100%. 100% ethanol is not so easy to get. Because normally when you distill ethanol, let's say you have ethanol in water, you distill it. Do you know the purest you can get ethanol by distillation? By distillation, you can only get 95%. There's 5% water that's very stubborn. It just wants to hold on to it. It's called an azeotrope. Normally, we can just purify things by distillation, but not ethanol, because ethanol, the purest you can get, 95%, 180 proof. So to get that remaining last 5% of water, they use other techniques, physical techniques like extraction, solvent extraction. But sometimes the solvents that they use for these extractions are carcinogenic or mutagenic, And so what it does is denatures the alcohol when they make it, because getting rid of that little bit of impurity, that residual extraction solvent is probably more expensive than it's worth. And so they just leave it. And so you don't want to drink this stuff. Well, it's good for us because, you know, they charge a very expensive tax for ethanol, which we I think we pay that for our 95% ethanol that we have. We also have 95% ethanol. It has a little paper thing, a little label.
What kind of tax do you pay on 95% ethanol?
I don't know. You know, and it's probably changes. I don't know how much it is,
Consumption.
but there's a little label over that's paid the tax, you know, the paper label that goes over it. So I assume it's one of those, you know, like the cigarette tax, alcohol tax. Thing. Well, anyway, what do you think about 95% ethanol? Ethanol, does it split up into hydroxide and some other cation? In other words, does the OH on ethanol break off? That's CH3, CH2, OH. Does this OH break off? The answer is no, the OH doesn't break off. That OH is what we call a polar covalent bond. And so it doesn't ionize here. Versus in an ionic bond, you would ionize, like sodium. If this were sodium, you know, there's going to be a tug of war for the electrons here. Carbon is a 2.4, oxygen is a 3.5. So oxygen is definitely a lot stronger, but not strong enough to completely strip the electrons off carbon. And so this is why we end up with a polar covalent. Whereas if this were sodium, sodium is like a 0.9. Oxygen is a 3.5 in terms of electronegativity, so oxygen is plenty strong enough to strip off the electrons off sodium. And so this bond does not ionize, and this is not considered a base, you know, ethanol. Potentially it might be an acid. Ethanol is not a great acid, you know, but there is a delta plus on this. When we're looking at acid-base properties, we look at formal charges. There are no formal charges in ethanol. There's a delta plus. You know, if we have a strong enough base, it could pluck that off. But it has to be quite a strong base to do that. Usually stronger than hydroxide. It would have to be something like amide or whatever. But ethanol is a molecular compound, and does it conduct electricity? No. There's plenty of mobility. Plenty of ethanol molecules. It just is lacking what? Charge. No charge. Well, maybe do you think water will be successful in plugging off a hydrogen or plugging off a hydroxide off ethanol?
No.
Or plugging off a hydrogen off carbon? No. And so when I add water to this and make aqueous ethanol, is anything going to happen for the conductivity? No. It wasn't plugged in. So,
I guess we'll never know.
yeah, we'll never know. But this would have been the result. Now it's plugged in. Do you see any electrical conductivity? No. So that's our ethanol. Okay, after ethanol comes what?
Glucose.
Not glucose.
Sugar.
Sugar. This is sucrose. Well, the ratio here, I don't know, but do you see the ratio between hydrogen and oxygen?
Yeah.
The ratio between hydrogen and oxygen is 2 to 1. And so this is called a carbohydrate. Carbohydrates will have a 2 to 1 ratio. It's not that they have water inside there, it's just weird that they have this kind of ratio here. Sucrose has got alcohol groups on there. It's a molecule. And so if I have solid sucrose, do you think it'll conduct electricity? No. What if I melt it and I have molten sugar? I have to be careful about melting things, you know, because if you start heating it too hot, what happens to the sugar?
It'll burn.
It'll burn, and melting is a physical change, and so we could re-solidify it and just get solid sugar again. But if I burn the sugar, that would be a chemical change. But people like burnt sugar, like caramelized sugar. Maybe not like charcoal, but if you melt it, do you think it will conduct electricity? So if you have molten sugar, you just have these, rather than these locked in a crystal lattice, and sugar melts at a low temperature, you'll just have these molecules and they'll have translational motion. But they're still lacking what? Charge. Yeah. What if I dissolve in water, sugar water? Does that conduct electricity? Well, it depends on what water I use. If it's tap water, yes. But if it's deionized water, no. And so you'll have to take my word for it because I don't have any sugar here. There's lots of sugar over there in the stockroom, but I don't know what happened to it here. But the thing we want to do is we want to just be able to predict it. You know, we want to make accurate predictions. And this saves us the work. You know, this saves me the work of walking over the stockroom, grabbing a bag of sugar, and coming back here. Because, you know, our prediction, are you pretty confident in that prediction? You say? Yeah. Okay. So that ends the conductivity part for part 1. Let's move on to part 2. What's number 1 of part 2? Acetic acid. Is it liquid, pure acetic acid, or is it aqueous acetic acid? It's aqueous. Acetic acid is actually a liquid in pure form. We call it glacial acetic acid. But this will be aqueous acetic acid. Is acetic acid a strong or weak?
Strong.
Strong? It's weak. Well, being a weak acid, what does that mean? That means it's not as good of a proton donor. It doesn't lose the proton so easily. And so what happens is water comes along and tries to pluck the proton off. Will it be successful in plucking 100% of the protons off? No. There's going to be a much more significant fight between water and acetate for that hydrogen. And so what happens is this lone pair gets pushed into this, and it knocks these, because you know hydrogen wants a duet, knocks those out. And so what we end up forming is this. What's the formal charge on this oxygen here now? -1. So we end up forming acetate. All the other formal charges are 0. And what's the formal charge on this oxygen here? +1. So what we have is we're going from a weaker acid, acetic acid, to a stronger acid, hydronium. And so this is unfavorable, going uphill. So the downhill direction is actually the reverse. This is the downhill direction. And what we end up with is something like this. We end up with about 99% this and about 1% this. It's actually less. This is greater than 99%. This is less than 1%. It's quite a steep hill to climb, so only about 1 or less % of the population can make it up that. Mm-hmm. This carbon here?
Yeah,
I was thinking ethanol, so that's why. Yeah, that's a good point. Carbon always fulfills the octet rule. You know. We can't go more than an octet with carbon. So, yeah, that definitely looked weird. I didn't notice it initially. All right, so we're going to form a small quantity of ions. These ions can conduct electricity, and we should see the light bulb light up. With that. Oh, here's my sugar. Do you want to see the sugar?
Yeah, sure.
Yeah, all right. What's that?
I said, we're all here.
Normally you don't pour it back, but this is only used for this. And this is a clean beaker. You see any? No. I could try to melt this, but I'll probably end up burning it. But you aren't going to see anything. And what if you dissolve it in water? No, let's see. No, nothing. I actually have 2 acetic acids here. This is called glacial acetic acid. This is 1 molar acetic acid. Glacial acetic acid, and I don't know the origin of the name glacial.
Isn't glacial the one? Is it ammonia anything?
What was that?
Is it glacial one? Yeah, C acid plus ammonia?
No. No, glacial is the word they give pure acetic acid.
Oh.
So this is pure acetic acid here. It's just a liquid. There's no water mixed in it. Well, actually there is a little bit of water because it's hard to get 100% pure when we live in a humid environment. So let's take a look at glacial. Glacial acetic acid has a strong vinegar odor to it. You can smell it?
Yeah.
Okay. Okay, let's take a look and see if this conducts. I don't want to contaminate it with water, so I'm going to dry off these electrodes. Yeah, it smells bad. Do you see much? I don't see much of anything. Let me cap this. So if I have glacial acetic acid, then I'm going to make some aqueous acetic acid. Normally, the safety rule, you always add acids to water. You don't add water to acids. Do you know why?
Reaction.
Because some heat is generated. And what happens is if you add water to this, the heat can superheat the water, cause it to boil rapidly into steam, and then you have little steam explosions. So if the water drop gets submerged here, the heat is all absorbed by the water, and it creates a little explosion, and then splattering happens. And so what we do is, to prevent this, we have a water heat sink, and so we add the acid to the water so that this water can act as a heat sink to absorb the heat that might be generated from this. All right, so now I have some aqueous acetic acid. Let's see what happens here. So we have some So what happened there? Ooh, this smells bad. This was just under my nose here. Let's move it. Okay, so this is aqueous acetic acid. Woo! Electrocution. Aqueous acetic acid conducts electricity. This is pure acetic acid. Do you see that? Did my hair stand up?
No.
No, okay, not yet.
You touch it a couple more times.
Yeah. All right. So tell me, what's going on? What would you say glacial acetic acid? Is it?
No charge.
Yeah. Basically, if you just have pure acetic acid, there's no charge. There's mobility. There's numbers. There's just no charge. If you have aqueous acetic acid, then what does the water do? The water tries to pluck the hydrogens off to make ions. And it's somewhat successful. You know, this 1%, this is pretty concentrated, so that's why the bulb lit up pretty high. But, you know, we had enough ions to generate a weak current there. And so this is what's going on here. This is called hydrolysis. When we have things react with water like this. Okay, what's next? All right, so in this case, we want to talk about the major and the minor species here. In pure acetic acid, the major species, actually the only species is acetic acid molecules. You know, do you think an acetic acid molecule and an acetic acid molecule are going to, react? No, they're both acids. They're both acids, right? They want what to react with?
A base.
A base. In aqueous acetic acid, we're going to have the major species. The major species are acetic acid molecules and water molecules. The minor species would be acetate ions and hydronium ions. And so here it makes sense to write minor species and major species. HCl, hydrochloric acid. Hydrochloric acid is a strong acid. Strong acids are too strong to exist in water. And so we aren't going to find any hydrogen chloride molecules in water. All the hydrogen chloride molecules will do what? Attack, well,
Break up and break up.
yeah. Actually, let me write it like this. So if I had any hydrogen chloride molecules, water has no problem. Strong acids are strong electron donors. Water has no problem plucking off all the hydrogens off hydrogen chloride. So much so that this is a one-way. This is like a trip down, some kind of roller coaster or whatever. But what we're going to get is we're going to get chloride and hydronium. And so it's such a steep and long downhill, very few of these will make it ever back up. I mean, it could happen, but normally what people just show is this is one way because so little will make it back up. Now, you can help that process along. If you want to make it back up, you can try to generate a gas. Because gases are driving forces for reaction as well. And let's find the hydrochloric acid. Okay, they put it in this one. All right, this is 1 molar hydrochloric acid, and let's see what this does here to this. The thing is, this is one way to get this to go backwards. One way to get this to go backwards is to leave the cap off. If you leave the cap off, then what happens is the hydrogen chloride molecules can escape off the surface. You'll smell it. You know what HCl smells like? It smells bad. It starts to burn, your nose and your throat. This 1 molar is not so bad, but you get to 6 molar, you can smell it. When you get to 12 molar, it definitely smells. You probably want to do it in the hood. Even 6 molar and 12 molar, definitely like to use the hood. 1 molar, I don't smell much of anything here. But what can happen is, okay, if you can drive off the HCl as a gas, then you can force this back up the hill. Does that make sense? Here. Eventually what happens is, if you leave the cap off, this is not going to be 1 molar. Eventually it's going to go flat as the HCl escapes.
HCl is just equivalent soda. It'll go flat eventually.
Yeah, it'll go flat eventually. Yeah. It doesn't bubble like, sparkling water because HCl is very soluble. Do you see that? Yeah. That's a strong electrolyte. Strong acids are strong electrolytes. Weak acids are weak electrolytes. It's pretty strong. So what we say here for this is, since this is one way, the major species are this, and we wouldn't even consider the HCl molecules would just be minor species 0. Strong electrolytes, we're just going to make the assumption they ionize 100%. That's not 100% accurate. In Chem 1B, we'll learn it more, but the amount is so small, it's insignificant.
So there will be no major minor species for the HCl.
Yes. No minor species for the HCl.
Does the same apply to the acetic acid aqueous?
No. There are minor species.
Okay.
Yeah. Those minor species are what's conducting the electricity in this apparatus. Let's go to sodium hydroxide. Now, sodium hydroxide, I treat, normally when people think sodium hydroxide, strong base, right? And strong bases are strong electrolyte. But I don't treat sodium hydroxide like that. When I look at sodium hydroxide, I see a sodium salt. And what do we know about sodium salts? That they're soluble. And so this is a group 1 salt. Group 1 salts are soluble. And soluble salts are strong electrolytes. So, strong electrolytes will split up into the ions here. And then what I have is strong base here. So strong base like this, bases hydrolyze water. They do not ionize. So let's look at a strong base and a weak base here. So the strong base is like hydroxide. And when we say hydrolyze, hydroxide and water come together. Do you know what they form?
Hydronium, hydroxide.
Not hydronium. If hydroxide plugs a hydrogen off, do you know what we form?
Water.
Water and hydroxide. Water and hydroxide. So there's no change here. Let's take another strong base. Give me another strong base, any strong base. Amide, okay. We'll go with amide. Do you know the formula for amide?
NH2 minus.
NH2 minus. This is a strong base. Strong bases hydrolyze water. Strong bases hydrolyze water completely. I wrote this one as a two-way, but this one's going to be one-way, and it's going to form what?
NOx plus hydrogen.
Not NOx. NOx would be NOx. What do bases want in Bronsted?
They want a proton. So it would be NH3 plus OH minus.
Yeah, NH3 plus OH minus. Bases are proton acceptors. So this is a one-way street. And so this is what came up with our rule. The strongest base that can exist in water is hydroxide. All strong bases hydrolyze water to form hydroxide. And so hydroxide will be the most. That we can get out of this. Weak bases, you would think weakly ionized. No, weak bases don't weakly ionize. Weak bases weakly hydrolyze. So here we have a weak base. It's going to weakly hydrolyze to form what? Ammonium and hydroxide, yeah. The difference between a strong base and a weak base is the amount of hydroxide that's produced. Strong bases produce a lot of hydroxide. Weak bases produce a little bit of hydroxide. It's harder for ammonia to pluck a hydrogen from water than amide is. And so this is weak. This is strong. So when we look at sodium hydroxide is a soluble salt. Soluble salts are strong electrolytes. Strong electrolytes are going to conduct, or they should conduct well, as long as there's sufficient concentration. And so let's go ahead and test our sodium hydroxide here. And what do we predict? Yeah. Strong conductivity, weak conductivity? Yeah, strong conductivity. Oh, this is dirty. All right, let's try this. Sodium hydroxide is a severe eye hazard. And so you don't want to splash this into your eyes. It has serious eye damage. Let's take a look at this. Oops. Well, I kept some HCl here. This HCl and sodium hydroxide make what? Yeah, salt and water. Did I tell you my high school chemistry teacher always said, HCl and sodium hydroxide make salt and water. So you can't drink HCl, you can't drink sodium hydroxide, but you can drink the product of that.
But he never drank it himself.
But he never drank it, yeah.
But wouldn't that equal seawater?
What's that?
Wouldn't that make seawater?
Yeah, like it doesn't make seawater is a more complex mixture. It makes salt water. You know, there's salt in the ocean, sodium chloride loss.
Wouldn't you have to mix exactly the right amounts?
Yes, that's right. You know, I'd want to get the burette out, and I'd want to just make sure it's in the right proportion. This is not in the right proportion because this is limiting reagent, excess reagent. Here, I just put a little bit of sodium hydroxide, but I had a lot of HCl in there, so I wouldn't drink this. Right? And that's why I don't think he ever, you know, he never did drink it. I was waiting for him to drink it, but he never did. But it would be kind of interesting to do that. I don't know.
One of these days. Almost perfect.
It's scary.
Yeah. Well, I'm not going to fill you with expectation here. I'm not.
We won't give
I don't feel. It's not that. It wouldn't be too difficult to do. But one, I don't want to drink phenolphthalein. I wouldn't use phenolphthalein as an indicator. I'd probably get a clean pH meter, pH probe, and then just adjust the pH to pH 7, and then I'll drink it.
use the litmus strip.
But yeah, I don't know about using litmus paper. You know, litmus paper is difficult. They have other kinds of pH paper that would be a little better for doing something like that. Okay, what's next?
NH3 ammonia aqueous.
Okay, ammonia aqueous. Aqueous ammonia. Here we go. What do you think about aqueous ammonia?
Conductive but weak.
Yes. It turns out it's in about the same as acetic acid, more or less. So this is greater than 99%. And this is less than 1% of the population. And so acetic acid is about as strong of an acid as ammonia is a base. Weaker acids and bases will have much higher population of unhydrolyzed and much smaller population. And then the stronger acid of the base, the more hydrolysis you expect. But let's take a look at ammonia. You compare that to sodium hydroxide, there's a pretty big difference. Okay. I'll just dump my ammonia in with my HCl to neutralize it. Ammonium salts don't smell so bad, so that's one way to kill off the odor. One way to detect ammonia is it has a very distinct odor to it. So the next one is acetic acid and ammonia. So this is just a reaction. Here. This is an acid-base reaction. So, for Bronsted acid-base, what we do is we inventory it. And so first we look at what's present. So we have acetic acid, we have ammonia, and we have one more. We have one more, which is water. And acetic acid is only an acid. Ammonia is both an acid and a base. So if we go along the acid chart, we can find ammonia on the left side and we can find ammonia on the right side. It's a much better base than it is an acid. But what it means is it can go either way. That is, ammonia can gain a proton. If ammonia gains a proton, then we form ammonium. But ammonia can also lose a proton. If ammonia loses a proton, do you know what we form? Amide, right. And amide is very unstable product. So This one isn't so favorable. This is much more favorable here. But it's both. Now the species that can do both is called amphoteric. And water is the same. Water can do both. But the interesting thing about water is it's equal in strength. And so it doesn't really matter which way water goes. Water, and it's just based on, statistics, probability. So water can gain a proton to form hydronium, and water can lose a proton to form hydroxide. And so it's amphoteric, and it's equally strong, acid as a base, whereas this is a much stronger base than acid. Over here. Okay, now we have these three acids. Which of these three acids do you think is the strongest?
Acetic.
Acetic. Which base do you think is the strongest of these two?
Ammonia.
Ammonia. That's correct. And so when we predict Bronsted, all we do is we transfer a proton from the acid to the base. I could do this with Lewis structures like we did over here earlier. But tell me what forms.
Acetate, ammonium.
Yeah. And so we're going to form ammonium and acetate. Like that.
One-way reaction.
This is one way. This is one way because there's a driving force. What we look at for downhill, at the bottom of the hill will be the weak species. At the top of the hill will be the strong species. And so when we're looking at this, we're going to compare. If we go forward, this is our acid, this is our base. If we go backwards, who's losing the proton, who's gaining the proton? If we go backwards, down.
Ammonium is losing.
Ammonium is losing, so that's our acid, and
Acetate is gaining.
acetate is gaining, so that's our base. Then we compare the strengths. Which one is a stronger acid, ammonium or acetic acid?
Acetic.
It turns out acetic acid. Acetic acid is orders of magnitude stronger. Although we don't have the chart here, but we could see that acetic acid is much higher than ammonium. Ammonium is much lower ranked. And so this is all we need. Because of the conjugate relationship, the bases must follow the same pattern. So it turns out that, yes, ammonia is a stronger base than acetate, which is a weaker base. And so which way is downhill in terms of energy?
Going from acetic ammonia
Yeah.
to ammonium and acetate.
So we expected there's a driving force for reaction. So this should go forward.
It would not be double.
Hmm?
It would not go both ways.
It'll go both ways. Yeah. It'll go both ways. This is a topic in chapter 4, near the end, chapter 4. Near the end of chapter 4, there's something called the extent of reaction. And the extent of reaction is like this. Let's say it's huge hill, like this. So when you look at the population down here, there's a negligible amount of population that can make it back up the hill. Negligible. But let's say that it wasn't such a big drop. Let's say this was the drop here. Now when we look at the population here, there's a much bigger population that can actually make it back up the hill. It's not favorable, but you have that small group that will make it back up the hill. And so sometimes some reactions don't go 100%. You cannot get 100% yield. It just won't happen. It won't happen because the reverse reaction starts to take place. So the best yield you can hope for some reactions might be like an 80% yield because 20% of the population makes it back up. Does that make sense? So the common causes of getting a lower getting a lower yield than the theoretical yield, and hence a percent yield less than 100%, is the most common one is losing some stuff. Like, did you scrape out all the precipitate out from the beaker? No, because it's going to take me hours, and so I didn't want to waste the time doing that. But another common reason for getting yields less than 100% is because some of these don't want to stay down here. If everybody stayed down here, then we're going to get 100% yield, in theory, right? But in some certain reactions, not everybody stays down here, and we cannot get 100% yield. No matter how hard we try, we can't, because some of them go back up. And so for those reactions, we say, okay, the typical yield for this reaction is 68%. So how much do you have to mix together to get the desired actual yield? You know, that kind of thing. Those are stoichiometry problems that we do. These reactions that are reversible like this, we have to do something different with the stoichiometry. You know, obviously we can experimentally measure, okay, what was our yield, percent yield from that, and then maybe use that. But the percent yield kind of changes depending on what the concentrations are. And so when we have this problem where not everybody stays as product like they should, we use Chem 1B style stoichiometry. And so that's it. So a lot of our reactions, like if I give sodium hydroxide and HCl, no problem. Sodium hydroxide and HCl are falling off a cliff. We're going to make salt and water. So I'm not going to worry about anything climbing back up this hill, because nothing's going to climb back up the hill. But when I get acids and bases that are a lot weaker, then I'm going to have trouble here. And so we can kind of get an idea, you know. It depends on how much weaker ammonium is than this. If ammonium is tremendously weaker, then yeah, it's pretty much going to just be one way. If ammonium is kind of close, then we're going to get a lot of back and forth. But for sure, this is going to favor this. You know, this is kind of the downhill direction here. What we do in Chem 1A, though, is we aren't going to deal with those kind of reactions. In Chem 1A, we're going to treat everything as black and white. If there's a driving force, then we're going to assume it happens 100%. There's none of this going back uphill. They're all going to stay downhill. And that's what we're going to use for predicting our stoichiometry. And if there's no driving force, we're going to just assume that nobody made it up the hill. You know, if there's no driving force, we're going up the hill, but it depends on how big that hill is. If the hill is just like a little hill versus a mountain, you know, there's a big difference there. If it's just a little hill, then maybe even a bunch of these can make it up. Like if you're a group within a group of bicyclists, a bunch of the bicyclists can make it up the little hill. But can a bunch of bicyclists make it up the big mountain? No, maybe none. You know. So in Chem 1A, when we do our stoichiometry, we're just going to assume that things, and we pick reactions with large driving forces. And we avoid certain reactions in stoichiometry problems because we're going to get the wrong answer, basically. Okay. In Chem 1B, then you can just do the proper calculation. All right, so we're doing acetic acid and ammonia next. And we're going to say that this reaction happens to a huge extent. It's actually orders of magnitude weaker. And so there's a really good driving force for this. And so we expect very little of the reactants left over. It's going to be mostly this. And so how's that going to change things? So what I want to do is I want to add acid to the ammonia. So let me find the ammonia here. Okay, do you see the ammonia? And then acetic acid is a weak acid too, so it'd be comparable in terms of brightness here. So I'm going to add acid.
The ammonia on the table is smoking.
Oh yeah. The ammonia on the table is smoking. Do you know why?
Because it types up.
I'll do it. Yeah, that was the glacial. You know what it is? Because I told you that HCl, a little bit of HCl can be driven off the surface, right? If I leave it uncapped. And ammonia is the same thing. Ammonia is a gas, and the ammonia can be driven off the surface as well. And so let me just show you really quick what's going on there. I don't have my 6 molar hydrochloric acid. I'm looking for 6 molar. I have to use 1 molar. Well, I guess there's plenty. Do you see the smoke coming off here? Can you?
No.
No? All right.
Mine said something, guys.
This is my ammonia, and let's see. If I get it close to this, you'll probably see the smoke. Maybe not. Let me open this. Acetic acid. Put that. I need to lay things out on the bench here. Do you see any smoke?
When you open
Yeah, when I opened it. It's because... Oh, here, this is better. Do you see the smoke now?
Yes.
Yeah. Do you smell the acetic acid? The vinegar? What do you smell? You're smelling molecules of vinegar, right, in gaseous form. And so this gaseous vinegar is going to react with ammonia. We have an acid base. And so do you know what that smoke is? That smoke is ammonium acetate, tiny, tiny crystals of ammonium acetate. And what I could do is I could put some surface here. Those crystals will deposit on the surface, and then I'll have ammonium acetate on my hand. I was going to make ammonium chloride, but my HCl is too dilute for that. All right, so I have my ammonia here, and I'm going to add some acetic acid.
Yes. Add the vinegar.
Okay. I'm going to add the vinegar. And the vinegar doesn't light it up very brightly either. And so I'm going to add acid. Add acid to try to control the heat. Make sure this doesn't splatter. Okay. So it got bright. It got bright because the population of ions just increased dramatically. So in this particular case, the major species would be the ions over here. And you could write these as the minor species if you think about reversible reactions. Chem 1b style. But it would be more like, 99% this and less than 1% that, probably. All right, let's take a look at part 3. These are all double replacement reactions. Double replacement reactions are AB plus CD. So lead 2 acetate plus sodium carbonate. What are we going to form? We're going to form lead 2 carbonate and sodium acetate. Lead 2 carbonate is a white PPT. And so let's go ahead and I'm going to do this one. Now I want you to do these in your notebook because they don't give you enough room to write anything here. So we have three types of equations that we deal with. One is I'm going to have, let's say, a beaker. In this beaker, I'm going to have lead 2 acetate solution, aqueous. Normally I don't write aqueous. And then I'm going to have another beaker of sodium carbonate, aqueous. So this is they call the whole formula, or just the conventional equation. I call it CE, just, our standard conventional equation. Now, lead 2 acetate, strong electrolyte, weak electrolyte, or non-electrolyte?
We, no.
It's soluble. All acetate salts are. Acetates, nitrates, and chlorates are all. This is a soluble salt. It's a strong electrolyte. That means in a beaker of this, I'm going to have lead 2 ions and how many acetate ions?
Minus 2.
2 acetates. And so in this beaker, I'm going to have, actually, I should have made it bigger. Lead 2 ions and then acetate. And these are going to be floating around. They have mobility. So this is called the ionic equation. This shows what the species are, the major species are. In the ionic equation, we list only the major species, not the minor species. Sodium carbonate, so all sodium salts are soluble. And so this is going to ionize into what? 2 sodiums and a carbonate. And so those are going to be independently moving about in solution here. Okay, now we do the double replacement. The double replacement says we're going to form lead 2 carbonate and sodium acetate. Okay, to balance this, I'll need 2 sodium acetates. Then it's balanced. Lead 2 carbonate, carbonates, phosphates, and chromates are all insoluble except for group 1 and ammonium. So this is going to precipitate out. All sodium salts are soluble, so this stays in solution. And so what we end up with here is we end up with a PPT of lead 2 carbonate solid. And then the sodium ions are just moving about, and the acetate ions are also in solution, moving about like that. So in the ionic equation, we list the major species. The major species in this case are going to be lead 2 carbonate solid and 2 sodiums and 2 acetates. Now, if I start writing aqueous, I have to continue writing aqueous for everything. And continuing to write aqueous for everything is a lot of work. There's so many species here that what I like to do is I like to just omit aqueous, and if it's non-aqueous, then I like to write in the state. So which ion combination was favorable? What ions like each other? Did the sodiums and the acetates come together and like bond with one another? No. The lead and the carbonate did. Just the lead and the carbonate. And so then we have our NIE, our net ionic equation, which just shows what ion combination was favorable. In this case, lead and carbonate, which precipitates out to lead 2 carbonate solid. So, there's another safety rule that Carmen brought up. the other day. And that is, when we grab a bottle of reagent, we like to grab it the same way each time. So here's my lead-2 acetate. And so normally what happens is there's spills. Do you see there's spills and there's dried up lead there? Lead-2 acetate? Yeah, and there's spills on the side. So we don't want spills all the way around this 360. So we just want spills on one side so when you grab it, you don't poison yourself. This is heavy metal poisoning here. But if I do get heavy metal poisoning, do not take me to get the EDTA therapy just yet. What?
We wouldn't want you to stop teaching.
Maybe I've already had lots of heavy metal poisoning, unfortunately. So does it matter which one I add to which? Should I add the sodium carbonate to the lead-2 acetate or the lead-2 acetate to the sodium carbonate, or it really doesn't matter? I wish I had gloves. If I had gloves then. Oh no, it's all right. Okay, the stopper here, this stopper is designed to hold between your fingers. You don't want to set this on the counter. If you set this on the counter, especially with this end down, you're going to contaminate your countertop. And you'll also contaminate this solution. You don't set these on the side, although you could. You know. There's other ones that have a flat top. Those can be set upside down on the counter. These are just meant to be held between your fingers. So I'm going to pour some lead-2 acetate. What is your observation for lead-2 acetate? Clear, colorless solution, which we give the abbreviation CCS. So lead ions have no color. Carbonate ions have no color. Let me just rinse off the lead I have here. Okay, now I'm going to get some sodium carbonate. And let's take a look at sodium carbonate, what it looks like. Here. This is my sodium carbonate. What would you describe this as? CCS. Okay, do you see all the dried up sodium carbonate on the mouth of the... I'm just going to leave it there. And normally we grab it by the label side, but sodium carbonate, I don't really worry about it. And then what do you predict is going to happen? Precipitate lead-2 carbonate. Do you see that? We got a cloudy white precipitate. Eventually that cloudy white precipitate will settle to the bottom of the test tube, like here. The precipitate will settle to the bottom, and above this we should have a CCS of sodium acetate, aqueous. We can do certain things to speed that up. One, we could filter this. Two, we could boil it. The same thing is we could boil it to coagulate the crystals, make them bigger so that they fall down. That's good. That's a common technique. Or three, we'll just let it sit. So I'm just going to let this sit. I'm going to call this test tube number 1. Let's go to number 15.
That's a big check.
Yeah. It is temporarily. Jump to 15. What are we going to add to this test tube number 1? Nitric acid. Let's predict what's going to happen first. So they want us to add it to the precipitate, but I'm just going to add it to the mixture. I don't want to filter out the precipitate, wash the precipitate, and then add it. No, it's too much work. So nitric acid and sodium acetate, it could be a reaction there. Actually, there is a reaction there. So if I didn't remove the sodium acetate, so I'm going to have aqueous sodium acetate plus nitric acid. This is an acid-base reaction, or it's a double replacement metathesis reaction. Let's treat it, if we can treat it as a double replacement, that's easier. So let's go ahead and do that. What's going to form here? We're going to form
Sodium nitrate.
sodium nitrate and acetic acid. Is there a driving force for this? So we look at the acid here. The acid here is nitric, the acid here is acetic. And we know that nitric acid is a strong acid and acetic acid is a weak acid. So this is definitely a stronger acid, a weaker acid. So we do have driving force here. So this is going to start to smell. Sodium acetate doesn't have a smell. Acetic acid does have a smell. So if I don't remove the sodium acetate solution here, it's already settling. Do you see that? I'm probably gonna smell some acetic acid. Right now I don't smell any acetic acid. I'll probably leave it all in there. Okay, so that's what we predict will form if I don't remove this. Normally what we do is, if I want to just react it with the precipitate here, I'd filter it, remove this solution, which we call the supernatant, and then wash the precipitate with copious amounts of water to rinse off any sodium acetate that might still be there, and then add it to this. So I'm going to take my lead 2 carbonate solid and add some nitric acid to this. What should form here?
Lead nitrate plus
Okay, lead 2 or lead 4 nitrate?
lead 2.
Okay, so that's positive 2 and nitrate's minus 1, so we need 2 nitrates. This is aqueous. And all nitrate salts are soluble. For aqueous, I'm not going to bother writing aqueous anymore. And carbonic acid, H2CO3. But we know that H2CO3 is unstable and immediately decomposes into what?
Water and carbon dioxide.
Yeah, water and CO2 gas. So what driving force do we have here, if any? 1, there's no precipitate. But 2, we are going from a stronger acid, nitric acid, to a weaker acid, carbonic acid, or CO2 is also an acid. It's not the water, it's the CO2. And so stronger acid to weaker acid, water and CO2. We also have gas formation. Gas formation or gas evolution is a driving force. So we have driving force for this reaction, 2 driving forces. All we need is 1 driving force. But in this case, we have 2 driving forces, which is even better, but not necessary for the reaction. But this reaction is not balanced. What's missing here to balance this? 2 nitric acids. Okay, now what I'm going to do is I'm going to do this. I forgot to do it for up here. Since I'm not going to remove the sodium acetate solution, let's do this. This is what I call the conventional equation, Ce. What would the ionic equation for this first one be? So sodium acetate, do I ionize or leave alone? Ionize. Sodium ions and acetate. What do I ionize? What we ionize are just the strong electrolytes. Leave everything else alone. And so the ionic equation, the major species are ionized strong electrolytes only. If it's a weak electrolyte, we don't ionize it, we just leave it alone. And if it's a non-electrolyte, we leave it alone. HNO3, ionized to H plus and NO3 minus. Sodium nitrate, ionized to sodium plus and NO3 minus. Acetic acid, yeah, acetic acid is weak acid, leave it alone. That's ionic equation. And then we go to the NIE, the net ionic equation. So which ions had a favorable combination here? And so what we have is we have things that are called spectators. Sodium ion didn't combine with anything. Nitrate ions didn't combine with anything. But the hydrogen ions and the acetate ions did combine. And so the H plus and the acetate like each other and form acetic acid. And so we should be able to smell that acetic acid. Okay, now let's do the same. This is the complete equation. What's the ionic equation look? So lead 2 carbonate, ionize or leave alone? Leave alone. It's not a soluble salt. Soluble salts, we ionize. Insoluble salts, we don't. Nitric acid, we ionize that. That's strong acid. When we ionize it, how many total hydrogens are we going to get?
2
Two.
hydrogens.
Yeah. And so this is going to give us 2 H pluses and how many total nitrates? 2 nitrates. Okay, lead 2 nitrate, ionize or leave alone? We ionize that. Soluble salt. Not all nitrate salts are soluble. And so this is going to make 1 lead and 2 nitrates. We have to make sure it's balanced because we don't want atoms to disappear. And then water, ionize or leave alone?
Leave alone.
Leave alone. And carbon dioxide?
Also leave alone.
Yeah. And so this would be the ionic equation. This is just showing the major species reacting in this. But not all those major species react. And so we'll get to the net ionic equation. And so what are the spectators? What didn't react? It looks like nitrate, and that's it. And so the net ionic equation here is we have some solid lead 2 carbonate precipitate being attacked by 2 H pluses to form Pb2 plus H2O liquid plus CO2 gas. Now there's stuff missing here. The spectators are missing. So when we look for balance, it's when we look for balance, we look for atom balance and charge balance. So the atoms are balanced, I think, yeah, and the charges are balanced because I have a total net charge on the left of +2 and a total net charge on the right of +2, and therefore it's balanced. So those are the 2 reactions that are going to be happening here because I'm not going to separate it. And so I'm going to just take my nitric acid and just pour it in here and see what happens. So I should see what's called, you know when you have bubbling gas, what do you call that? Effervescence. I should see some effervescence. Let's see if I see that. Can you guys see it all right? Yeah, I see it and I can hear it, the fizzing. Do you see the bubbles? There's bubble formation. I don't know if you guys see it.
What's the abbreviation for effervescence?
EFF. It's hard to detect the smell of acetic acid vinegar. I don't really smell it, but it should be there. All right, this contains heavy metal, and I should dump this into a waste jug. It contains lead.
Did the precipitate vanish?
Yeah, the precipitate vanished. So there's no more solid left here. I had an excess of nitric acid. If I didn't add enough, then I wouldn't have dissolved all of it. Since there was an excess. I'll put this here. Okay, now we're going to kind of repeat this reaction, but instead of using sodium carbonate, we're going to use what? This will be number 2,
Sulfuric acid.
sulfuric acid. So I have my sulfuric acid. Sulfuric acid is a CCS. This is 3 molar sulfuric acid here. CCS. So I'm going to get my lead to acetate. Oh shoot! Just grab the one side of this. So if you end up probably should wash. If you end up coming into contact with stuff, you should wash and rinse for how long? 15 minutes. Maybe it's time for a 15-minute break. Problem with lead 2 acetate is soluble. If this were like lead 2, like some insoluble lead salt, then I wouldn't worry so much about it. But I barely contacted it, so that's probably adequate. I think I've been exposed to a lot more lead because back in the old days, did you know they used to have lead in gasoline?
Yeah, lead in paint.
Yeah, they had lead in paint, lead pipes, etc. So everybody's suffered from lead poisoning back then. All right, now I'm going to take my sulfuric acid, and what do you expect to happen? So, one of the things we want to do is just be able to predict what's going to happen. So let's go ahead and predict what's going to happen before we actually do it. And so we're going to take our lead acetate and react it with sulfuric acid. And what does this form? Acetic acid and lead 2 sulfate. So lead 2 sulfate and acetic acid. Is there a driving force for this? Yeah. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So lead is one of the exceptions. Most sulfates are soluble, but lead isn't. And so lead 2 sulfate should precipitate. Actually, we have more than one driving force. All we need is one driving force, and this is it, precipitation.
Strong acid to weak acid?
Yeah, stronger acid to weaker acid. It doesn't always have to be strong. In this case, it is a strong acid. Is this balanced? Yeah, 2 acetic acids. Now it's balanced. So what we expect is to precipitate. Now lead doesn't have color to it, and sulfate doesn't have color to it. And so lead 2 sulfate is expected to be what color?
Clear.
Yeah, colorless or white. So I have my sulfuric acid here. What is wrong with my lead 2 acetate?
There's more than lead in.
Yeah. Well, let's see what happens here. This test tube probably wasn't clean like I thought, but it's all right because we got a lot more white, cloudy precipitate. Okay, again, I'm not going to wait for this precipitate to settle. It's going to take too much time, and I'm not going to boil it. I guess I could. I could heat it up. And then pour it off. Actually, maybe I'll do that. No, I'm not going to do that. It's too much work. So, what are we going to do with this? So let's jump to number let's jump to number 16. Yeah, I'm sorry, there's no number 16, so you're going to make number 16. You know what number 16 is going to be? Number 16 is we're going to add nitric acid to our lead 2 sulfate precipitate and then see what happens. Well, before I do that, this is the CE. Let me write the IE for this. Lead 2 acetate is a soluble salt, so that's going to ionize. Sulfuric acid is a strong acid, so that should ionize. But the question is, what does it ionize to? In other words, this is what we call a diprotic acid. It has 2 acid hydrogens. Do both of the acid hydrogens break off? Or one of them? Actually, one of them breaks off easily.
H plus.
However, the second one does not, because HSO4 minus, is that one of the 7 common strong acids that you memorized? No. HSO4 minus is a weak acid.
So it would be bicarbonate, right?
Bisulfate, right. And so bisulfate is not a strong acid. Bisulfate is a weak acid. It being a weak acid only partially ionizes. And when we do ionic equations, we only do the strong electrolytes. And so weak electrolytes like HSO4 minus we leave alone. So this is really weird because people like to break this up like this. People like to break off both H pluses to get 2H plus plus a sulfate. But I would rather have you not do that. You know, I'd rather have you write it like this, even though it's a bit of a hassle. When it reacts, we need something else to pluck the proton off. This proton can easily be plucked off not by water. This proton can easily be plucked off by a base stronger than water. Actually, if I'm not going to bring it up, but we need a base that's stronger than sulfate. Any base that's stronger than sulfate can pluck this proton off, like carbonate, whatever. But when we're doing ionic equation like this, you know, these are just beakers. And this is just water. And water is only going to successfully pull off the first one completely. The second one, water can pluck off about 10% of that. But that leaves 90% bisulfate, so we'll just leave it as bisulfate. Okay, lead 2 sulfate, do we ionize that or leave it alone? Leave it alone. And acetic acid, do we ionize that or leave it alone? Leave it alone. Yeah. Acetic acid is a weak acid, just like bisulfate's a weak acid, so we leave those 2 alone. And so when we have multiprotic acids, we just break them off one at a time and see what we're left with. And so what would the NIE? And so what are the spectators? Looks like, what are the spectators in this? None. And so the NIE and the IE are the same for this. All right. Now, what do we have in solution here? In solution, I have acetic acid. So I might be able to smell it. I might not. Depends on how concentrated it is. But what happens if I add nitric acid to acetic acid? Because I'm not going to separate out the precipitate. Although the precipitate's settling pretty well at the bottom of the test tube now, there's still a whole bunch up here. It's still very cloudy. And so I'm going to have some acetic acid plus nitric acid. What's going to form here? Acetic acid, nitric acid. Therefore, we say NR. NR. They're both acids. They're okay to hang out. Except that's acid-base properties. There's one other property, though, and that is redox. Because in terms of metathesis, it's the same. You know, in terms of acid-base, it's the same. But in terms of redox, nitric is an oxidizer, and acetate is a reducer. And so there could be a potential redox reaction here. So if I heated this up, heated up or, did something, I could end up generating like CO2, oxidize the acetate all the way to CO2. Does that make sense? Or maybe carbon monoxide, or maybe some other weird species, partial oxidation. And so there could be some redox chemistry happening here. So I'll be aware of that. It depends. The more concentrated the nitric acid, the more likely I could have a reaction. But I'm not going to use concentrated stuff. The nitric acid I'm going to use is fairly dilute. Okay, so we predict there's going to be no reaction. What about with the lead-2 sulfate? How will nitric acid react with lead-2 sulfate? And so we'll take our lead-2 sulfate solid plus nitric acid, and what do you predict?
Sulfuric acid, lead-2.
Yes. We expect to form sulfuric acid and lead-2 nitrate. So do we have a driving force here? Are we going from stronger acid to weaker acid? Why not?
They're both equal.
They're both, are you sure they're both equal? Let me take a look at the acid chart here. Just verify that here. So when I look at the acid chart, I'm going from nitric acid to sulfuric. And so it looks like I'm going from a weaker acid to a stronger acid. True or false? False. False. That's good because you know the effect. What was that effect called? The effect. The leveling effect. The leveling effect means these are tied. Equal in water. So the leveling effect. And so that's not going to be a driving force. Did we get a precipitate?
Yeah.
No. No. And so these acids are equal. So strong acid to strong acid equal. No precipitate. Nitrate salts are all soluble. And sulfuric acid is soluble. Did we form a gas? No gas. Sulfuric acid does, but sulfuric acid does not. Sulfuric acid decomposes into H2O and SO2. And therefore, we expect no reaction. So this is number 16. When I add the nitric acid to this, I expect no reaction. So let's see what happens here. You see anything happening? No, nothing happening. And so NR for that. All right, let's take a break now, and then we'll complete this lab and then start the other one.
Do I get free check all of my chemical balances?
Number of the last one here. It's not exact balance. This is wrong equation. I'm going to do that one today. So we'll do it pretty soon.
See, you know, PT and now, is that your?
Gas.
Yes.
Oh, yeah. Can you turn it on? Oh, the exam I'm gonna give tomorrow. I'll give it that, yeah.
Okay. And want to look over like the legislation?
Okay, that looks fine. For the calculations, you just have to show one representative calculation,
Oh.
so you don't have to necessarily do that. I just want to see what conversion factors you're using, but this is good, the way you have it. Yeah, that's fine. Thanks. Oh yeah, you can just leave it from here.
Professor, I want to ask, how long do you think the lab that I need to make up is going to take? Because like, I talked to the lady today, and she's like, to do both parts, it's going to like take a while, but then I can only make it after my math class,
What time does your math class end at?
3:45.
3:45.
And I remember you said you have to leave at like 4:50.
Yeah.
Okay.
So you have one. Do you want to do it over 2 periods, or do you want to do it just in 1 period?
It doesn't matter to me, it's just like whatever works best for like stopping your schedule.
Let's see, 3:45. What you could do is you could just start it over here and then just leave it out.
Okay.
You don't have to clean it up and you don't have to return it, but you can just get started on it there and then just leave it out.
And then
It's going to take more than 1 day.
Okay.
You only have 1 hour.
So
At
first
least
part
you-
1 hour, and then the second part.
No. The first part's probably going to take more than 1 hour.
Oh, okay.
You'll have to make it up over, can you come back again for, on Monday
Yeah.
as well, and also in the future, possibly?
Okay. Do I need to tell them that like I'm gonna leave it out? Okay.
You can just tell them, no, you don't have to tell them, because they're gonna probably leave. I'm just gonna, just leave it out into a little note that's yours ongoing.
Okay.
Wait, so it's this times. I don't know. Because I think you're supposed to
I want a poster with like a funny picture. You're gonna get a poster of your life and see the poster. Well, I'm gonna do it. No, I want it now. Excuse me.
yeah, I have to go back.
Doing like, you know, like do like those like exercises. Yeah, literally.
Oh, yeah, because this is a math to try to keep it below that. Yeah, that's what you use.
Okay, we forgot. That makes sense. You did it right.
I was trying to calculate.
Crazy close.
Oh, it's so good.
Here you go. Sit.
That's minimum.
Okay. Sit all the way. Sit. No. Don't. Sit. Sit for a few minutes. Oh yeah.
So your guys' titration. Yeah. Things do.
Oh wait.
We have different elements.
Yeah.
This should be more or less.
0 A's.
My only problem is that at some point I got lost in my math. So whether or not that top part should be totally up to the
It's like if you push it, it doesn't
The
go
rest of
down.
it does.
Or that's when I was like American. When I was long medium.
Oh, you should have seen me in Chem 4. You want to know why I called it the first time we did it? I said titration from the teacher, right? Because I didn't realize that it was titration. Yes, titration.
What about
How'd you get the stock on to help you with fetal? It took me 3 minutes.
fetal?
Absolutely, because I originally called it PHPH, and that's not correct.
I said what I said.
Apparently called it PHPH.
You want my numbers?
Whether or not it's right.
Get out of here.
It should be, yeah. I lied if I did. I checked my math. Where did it sit? So,
think I might have left it in my dad's.
So,
But it's over here. I turned it in. Zero eight.
the ending, I know it's correct. The beginning, that's the one. I don't, that's how you cross-check it.
Oh yeah, 0.1. I got 0.8. Oh, so you're in.
I was doing Chem.
Did like 47.
I think we did all the research, so I just had to, copy and paste.
How many grams per mole? This, I looked it up.
No, it's
I think this is right. It's supposed to be 0.08. This is correct. This is
Unless it goes away like
yeah.
I think it just uses 2 milliliters. There's too much space. No, I think it uses too much space, but I was titrating. Or maybe not.
Okay, let's take a look at number 5. Can you predict what's going to happen with number 5? And so in other words, write out the complete equation, the ionic equation, and net ionic equation for number 5.
I'm rewriting my homework so that's more cohesive because last time all of my work was so
Oh, okay.
not cohesive.
You know, does somebody have it? You have it? What did you get, Lily?
Should I do the balance one?
Yeah, let's do the complete first.
Okay. 2 iron 3 nitrate
2 iron 3 nitrates
plus 3 sodium carbonate,
with 3 sodium carbonates.
and that goes to 6 sodium nitrate
6 sodium nitrates.
plus iron 3 carbonate solid.
Iron 3 carbonate solid. What's the formula for iron 3 carbonate?
Fe2CO3, and there's 3 of those.
Is that what others got? Anybody else get something else different?
Yeah, that's what.
Okay. All right. What did you get for your ionic equation?
Everything dissolves except for the solid.
Okay. So, what do you have first? The species.
2 iron 3 plus ions plus 6 nitrate ions plus 6 sodium ions plus 2 carbonate ions, and that goes to 6 sodium ions plus 6 nitrate ions plus iron.
Okay. One thing that people forget a lot is the charge. You have to write the charges on these. The other thing is balancing them. 2:6 ratio, whatever. Okay, for your NIE, what did you have?
2 iron 3.
Oh, did I get this wrong?
Oh yeah, that one should be
2 iron 3s.
plus 3 carbonates. That goes to iron 3.
Solid. Okay. And the driving force? Yeah. There's only one driving force. This is precipitation here. Yeah. Oops. All right. So here we have the reaction. This would be number 5. So let's take a look at the color of iron 3 nitrate solution. Nitrate's colorless. Okay, this has a different type of stopper. Do you see it's flat on the top, so I can't pinch it between my fingers easily. And so these ones you just set on top of the counter upside down like this, so we don't contaminate. This is called a ground glass joint. And so it fits very nicely on the top here. And you can see the glass here has been sanded, ground down. They also call this ferric nitrate. What's ferrous nitrate? If this is ferric nitrate, what is ferrous nitrate? Iron 2 nitrate. Iron 2 has a different color. Iron 3, do you know what the color is? I guess yellow, would you say? Iron 2 is green. It was a little different color. What color do you think the precipitate's going to be? Yeah, probably something like yellow. We'll try that. The sodium carbonate, this is a ground glass joint as well. Inverted stopper. Let's see what happens with the precipitate. Okay. It's kind of an orange, right? Rust-colored precipitate. So what I'm going to do is I'm going to add excess carbonate to make sure I precipitate out all the iron. And that's going to leave me with a sodium nitrate solution on the top. The sodium nitrate solution does it have any color? No. So the sodium nitrate should be a CCS, and we have this orange-brown precipitate here. One thing about carbonates, whether they're aqueous or solids, carbonates can be attacked by acid. And so I'm going to use a weak acid this kind. Do you think, last time I used a strong acid for number 16, we'll call this number, what should we call this? I'm going to call this number 17, I guess. Number 17, do you think acetic acid's enough to react with the iron 3 carbonate and acetic acid? Well, why don't you do that? Do this equation, number 17 for me. Iron 3 carbonate, the precipitate that we just formed, plus acetic acid. What do you expect to form? Or will there be no reaction?
That's the number 17. Right?
That's number 17. Are we on 17 for numbering? Yeah. Yeah, okay, call that number 17 in your notes. And do the same thing. I want the CE, the IE, and the NIE only for, last time we looked at, sodium nitrate's pretty unreactive in metathesis. Doesn't react. And so we're just going to look at the product of this, iron 3 carbonate, the solid product, plus acetic acid. So Iron 3 carbonate plus acetic acid. Tell me what should happen. Yeah. So what we expect to happen with iron 3 carbonate, the iron 3 carbonate should be attacked. Is there a driving force for this? Yeah, what are the driving forces for this? CO2 gas. We only need one, so gas formation, yes. And then we can compare. Which one do you think is a stronger acid, acetic acid or carbonic, CO2? Like carbonated water. Carbonated water versus acetic acid, which one do you think is stronger? Acetic. And so we're also going from stronger acid to weaker acid. Okay, so let's go ahead and take our iron 3 carbonate. It's settled somewhat. On the top, you can see it's starting to form a CCS a little bit. Or maybe I didn't add enough carbonate. It looks like there's still some yellow there. If I still see some yellow in solution, that means I have excess iron 3. I wanted excess carbonate, so I just didn't add enough, but that's all right. And then I'm going to get my acetic acid, and let's see what happens with this. What do you expect to observe? You expect to observe bubbles. Let's see if we get. This is with my 1 molar acetic acid. Do you see bubbles?
I saw a little forward you made, but that's about it.
Yeah, maybe my acetic acid has gone flat. I'm going to use a little bit more concentrated acid, acetic acid. Do I have the 6 molar acetic acid? 1 molar should have done it.
Not the glacial.
Yeah, it looks like I only have glacial acetic acid. I don't want to use glacial acetic acid, but I'll just add it very carefully. Glacial acetic acid is concentrated, so I'm going to add it slowly. You should add acid slowly, so any heat that's generated, these are exothermic reactions, can dissipate. Okay, I have a lot more bubbles forming. Do you see what happened? Do you see any more precipitate?
No, I don't see any percent.
No, there's no precipitate. There are bubbles floating in there. This is how you're supposed to mix test tubes when you don't have a stir rod. You're supposed to tap it like this.
Oh, would you like a stir rod, sir?
No, thanks. I don't want a stir rod because that means I have to clean a stir rod in addition to a test tube. But thanks for the offer, though. So what happens is now we have, it's a little darker than it was before, but the precipitate's disappeared. Can you see that? And it's been replaced by kind of an orange-brown solution. This orange-brown solution is just iron 3. And so that's what we expected here. The iron 3 is going to lead to an orange or yellow solution. And acetate's colorless. So we got that. Okay, next. Next we're going to have iron 3 nitrate plus sulfuric acid. What's going to form? Iron 3 sulfate. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So are you going to see a precipitate of iron 3 sulfate?
No.
No. We're doing number 6. Yeah. And what else are we going to form? Hydrogen nitrate, aka nitric acid. Are we going from stronger to weaker acid? No, because of the leveling effect. The leveling effect means that we ignore this. So when we look at this, sulfuric acid is a stronger acid than nitric. But because of the leveling effect, they're going to be a tie. Therefore, we expect that's not going to be a driving force. Is there any gas formation? No. And so what that means is there any driving force? No, there's no driving force. And so what I do is I'm going to add this and I expect nothing to happen. Let's take a look. But indeed, what happened to the color? It is now. It was a lot darker before. Now it's a lot more colorless. And we look for heat. I don't feel much heat. There will be heat. Whenever you add sulfuric acid to water, there's heat generated. But the color depends on the pH of the solution. There's iron 3. Iron 3 is a weird one. Do you see iron 3 here? This is iron 3 in water. What happens is the water surround, we call this solvation or hydration. And normally when we have ions, the waters kind of solvate or hydrate around the ion. But these hydrate so strongly that iron 3 turns out to be an acid. And so this is why the color is kind of pH dependent for this. Because iron 3 in water turns out to be a stronger acid than nitrous acid and a weaker acid than phosphoric acid. It's weird. And so what's happening with the color here is due to the iron 3, but the metathesis reaction that we had is correct. There is no reaction here. Now the reaction that we have with the iron 3 here, that's more Chem 1b. That's a Lewis acid-base reaction. And we look at those in more detail in Chem 1b. And so essentially, yeah, the color did change. It did look like there was a chemical reaction, and there was, but it really wasn't a chemical reaction. It was just differences in color based on the pH and what we have here. In a way, it wasn't really a chemical reaction. Okay. After that, what do we have next? Number 7 is iron 3 nitrate with
Sodium hydroxide.
So what do you expect to form? You expect to form iron 3 hydroxide. Hydroxides are all insoluble except for which one? Group 1, ammonium. Not all group 2. Just 3 of the group 2 members. Group 1, hydroxides are all insoluble except for group 1, ammonium, and calcium, strontium, and barium. So iron 3 is not one of the exceptions. So what we expect to form here is a precipitate of iron 3 hydroxide. And so let's see if that's the case. So I'll take my sodium hydroxide, which I have here. Sodium hydroxide is a CCS. You guys use this for the titration. I'm going to use 6 molar here and see what happens. Do I get a precipitate? What color do you predict the precipitate be? Yellow.
Lighter yellow.
You see the precipitate there?
Yeah.
It's kind of a brown, orange-brown precipitate. So I'll add a little bit more sodium hydroxide to generate some more precipitate. And then I'm going to mix this by doing this. This is actually the proper technique for mixing in test tubes. You're supposed to flick them like this. The reason is if you have stir rods, cross-contamination can be a problem, and also losing.
So is there no reaction in that, or?
No, there's definitely a precipitate.
Oh.
What is this? Do you see when it gets cloudy like that, that's a precipitate.
Oh.
You can see through it. Eventually that precipitate will settle down to the bottom of the test tube, but we're not waiting for that to happen.
It's like a rust color?
It's a rust-colored precipitate, exactly. What's the other product of this reaction? The precipitate and?
Oh,
Sodium nitrate.
Sodium nitrate. Does sodium nitrate have any color? No, so we'd expect a CCS once this precipitate settles down. All right, so I have iron 3 hydroxide, and is that a strong base or weak base, iron 3 hydroxide?
Wait, no, all hydroxide.
So what we're going to do is, okay, have this as, what number are we on now? 17, 18? We're on 18 for the extras? Okay. Number 18, we're going to take this rust-colored precipitate of iron 3 hydroxide solid, and then we're going to add an acid to it. What acid should I use? I could pick any. I could pick HCl. I could pick nitric acid. I could pick sulfuric acid. Or I could pick acetic acid. Which one should I pick? HCl? All right. What's going to form here? Okay, I'm going to form water and iron 3 chloride. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. So iron 3 chloride will not precipitate. So we've got no precipitation. What's the driving force for this reaction?
Water. No.
Yeah, stronger acid, HCl2, weaker acid, water. And so I expect the, if I add HCl, I expect the precipitate to dissolve. Correct? And so let's see if that happens here. So I have some hydrochloric acid, which is CCS. And let's go ahead and pour this in here and see what we get.
We're doing hydrochloric.
Oops, that was a mess. Pour it over the sink. I added, the problem is when I did the initial precipitation, what did I add excess of? When I did the initial precipitation, I took my iron 3 nitrate plus excess sodium hydroxide. And now I added a bunch of HCl, but I don't see the precipitate dissolving. And the reason is because I added so much excess sodium hydroxide that first I have to kill off all the excess sodium hydroxide I added, and then the HCl can attack my precipitate.
Do you have an HCl now?
Yeah. Well, in this, I'm not going to form any Cl, but I want to get more concentrated HCl. So I want to grab my 6 molar HCl and see. Because I use 6 molar sodium hydroxide. And so if I'm trying to neutralize 6 molar sodium hydroxide with 1 molar HCl, I'm going to have to use 6 times as much. Well, test tube is, I'm not going to be able to get that in there. And so my backup plan is I don't have any 1 molar. I'm just going to use 6 molar nitric acid. If I use 6 molar nitric acid, is that going to be a problem? No, because I'll form, rather than iron 3 chloride, I'm going to form iron 3 nitrate. So I'm going to get a mix. And so I'm going to use 2 different acids because this is 6 molar, so I don't have to add. I'm not going to have enough space to add the HCl. This is excess reagent, limiting reagent issues. Okay, there it goes. Do you see the nitric acid? Cleared it out. Now I have a mix. Oops, I didn't get all of it. There's some down there. Let's see if I can tap that. Well, here's what I'm going to do. You know what that's called? A decant. So I'm going to decant some of the solution on the top. Just pour it off. There's a trap in here. I mean, this is iron salt, so it's not going to be too damaging. There's a trap underneath the building that neutralizes the acids and bases. So now I have enough. Okay, so now it reverted back to, what's that? The yellow color is iron 3 ions in solution. All right, how much time do we have here?
40 minutes.
Okay, the next one we're going to go to is number 8.
It's not right.
That was number 18, I guess. Okay, number 8. What do you predict is going to happen there? Ammonium is a cation. Ammonia is a neutral molecule. And so how can it participate in metathesis reactions? The reason it can participate in metathesis reactions is ammonia is also a weak base. And what do weak bases do?
They want protons.
Yeah.
So they give away protons.
They don't give away protons. They take protons, but not 100%. Weak bases in water do what? Hydrolyze. So weak bases hydrolyze water to form what?
OH minus.
And NH4 plus and OH minus. Now, it's a weak base, so this is like 99%, and this is like 1%. But the major species here are ammonia and water. So if you went to the chemical store and you wanted to buy some ammonium, this is ammonium hydroxide. You went to the chemical store and you go to buy ammonium hydroxide and they give you a bottle. And then you take it home and you go, hey, wait a minute. This is 99% ammonia. I bought ammonium hydroxide. And so you go back to the store and you return it. And so they give you a new bottle. And you take that home, and the new bottle comes out 99% ammonia, 1% ammonium hydroxide, so you're thinking you got ripped off, and you got to go back again. And then you can write bad reviews or whatever else on Yelp. You know, you got ripped off. But did you really get ripped off? No, because you aren't going to be able to get a bottle of ammonium hydroxide, right? Because ammonium hydroxide is one of those ones that are unstable and decompose into ammonia and water. And so the situation here is most of the population is going to be down here, ammonia and water. It's just a small percentage of the population that's going to be able to react to form ammonium and hydroxide. But this is called a dynamic equilibrium. So let's say I had 1%. Well, that stays at 1% because what happens is ammonium and hydroxide decompose. Ammonium is an acid, hydroxide is a strong base. And so it decomposes back to this. But as soon as some of these fall back down here, they're replaced by a new set formed from a reaction up here. So we reach a state of dynamic equilibrium. And so we maintain a steady concentration of ammonium and hydroxide in water. And we can measure it. You know, it comes out to something like that. Well, is this tiny bit of ions enough to react? Did you see those ions were those ions enough to light up the light bulb?
Yes.
Yes. We saw it was dim, but it was enough to light up the light bulb. And so what that means is this. It means that if we have ammonia and water, these are our major species, but our minor species is going to be ammonium hydroxide. That's our minor species. But normally we don't write our minor species in chemical equations because if you went to the chemical store and you asked for ammonium hydroxide, they're probably going to say, sorry, we don't have it. And then you check back a month later and they still don't have it in stock. And in fact, they're never going to have it in stock. So hopefully the chemical supply salesperson tells you that really you aren't going to be able to buy it. Instead, you could buy ammonia. And so they can offer you some ammonia and water instead. And so this is why we're going to leave it as ammonia and water, but in reality it's ammonium and hydroxide ions that are going to react, that are formed from hydrolysis. And so what this means is we're going to go back to an AB plus CD pattern here. And so if we have an AB plus CD pattern, what forms? Ammonium nitrate and iron 3 hydroxide. Now the population is kind of small, but you know, if we eliminate some of the hydroxide from this, then more will come back to replace it. You know, you can't stop the collisions. And so if we lose some hydroxide, then there'll be more reaction to replenish that hydroxide, and therefore we should be able to get a reaction here. Now ammonium nitrate, all ammonium salts are soluble, all nitrate salts are soluble, so there's no precipitate here, but hydroxides are insoluble except for which ones? Hydroxides are insoluble except for group 1, ammonium, and calcium, strontium, barium. So this is going to precipitate. So we expect to precipitate iron 3 hydroxide. We saw that before. So there's driving force for this. Therefore, we should balance it. Now, when we balance it, it's easier to balance it using ammonium hydroxide. So how many ammonium hydroxides will I need here? 3. And that's going to give me how many ammonium nitrates? 3. Okay, if I have 3 ammonium hydroxides, that's going to decompose into 3 ammonias and 3 waters. And so the CE for this is going to look like this. We don't write the ammonium hydroxide in our CE. Some people do, you know, because that's really what's reacting in this metathesis reaction. And so I can't argue with that. But usually what we do is we write the major species of the species that we're going to go buy at the chemical manufacturer. Okay, that's our CE. What's our IE for this? Fe3 plus 3 nitrates, NO3 minus, plus, what do we do with ammonia? Keep it. Water we keep. Ammonium nitrate. What do we do with that? Break it apart. We're going to have 3 ammoniums and 3 nitrates. Iron 3 hydroxide? Leave it alone. We form ammonium nitrate here, but ammonium nitrate aqueous is going to be a lot more stable than hot, solid ammonium nitrate, pure. So we don't worry too much about an explosion here. All right, what's the spectator? Nitrate. What about ammonia? Is that a spectator? Is ammonia and ammonium, are they the same? No, ammonia is a base, ammonium is an acid. Actually, ammonia is amphoteric, but keep that. So this, the Ni is going to be iron 3 plus 3 ammonias plus 3 waters is going to yield 3 ammoniums plus FeOH3 solid precipitate there. And so ammonia can supply a little bit of hydroxide, you know, and hydroxide likes iron 3. And so let's take a look at this reaction. So I have my iron 3, and I'm going to get some ammonia here. I'm going to use the 1 molar ammonia, see if that's enough here. And ammonia supplies a little bit of hydroxide. Is it enough? And the answer is yes, it's enough. And so I get a rust-colored precipitate of iron 3 hydroxide. I can use any acid to eliminate that, dissolve this precipitate. So let's grab an acid. What acid do I have? Sulfuric. Oh, that's a good idea. Let's try sulfuric acid. The sulfuric is 3 molar, so I don't have to add too much. So I'll just carefully add my sulfuric acid. Let's see if it dissolves. And it did. So I'm back to...
So it's a clear to clear solution.
Well, it's actually yellow, but it's pretty dilute, so you don't really see the yellow here.
That's for number 8, right?
Hmm? This is an extra bonus reaction. You guys get the bonus reaction. Number 19, right?
That's for number 8, right?
Yeah, that's for number 8.
Alright.
Yeah,
This would be 19, or are we not right?
19. 19 would be iron 3 hydroxide plus sulfuric acid. That would be 19. All right, let's look at number 9. Ammonium acetate plus sulfuric acid. What is that going to produce? Ammonium acetate plus sulfuric acid is going to make ammonium sulfate. Okay, ammonium salts are all soluble, no precipitate. And acetic acid. Acetic acid is a weak acid, so we're going from a stronger acid to weaker acid. But we aren't going to see any precipitate. So what we look for in that particular one is just heat. You know, sulfuric acid. Number 19 was iron 3 hydroxide solid plus H2SO4. And what it forms is iron 3 sulfate, aqueous, plus H2O. So we're going from stronger acid to weaker acid. No precipitate there.
For number 19, was it form hydronium and sulfate to OH? Or would that just be water plus H?
It would just be hydroxide plus H. OH minus plus H plus gives us. So we need 2 of them. This is not balanced.
Oh, okay.
Yeah. But the products, then we have to balance it. The products are going to be Fe. Okay. What is the formula for iron 3 sulfate?
Fe2SO4.
Yeah, Fe2SO4 There's a trick. We use the charge on iron for the subscript for sulfate, and the charge on sulfate is a subscript for iron. We just do that trick. And the other one is HOH. HOH is just water, H2O, and then we balance it. Okay. So sulfuric acid plus sodium hydroxide. Oh, actually, was that it? What was the one we were looking at?
We were looking at ammonium carbon plus sulfuric.
Oh, ammonium acetate
Ammonium acetate.
plus sulfuric acid. All right, let me do that really quick here. So, ammonium acetate, what does it look like? CCS. So I'll pour in some ammonium acetate in here, and then I'm going to add some sulfuric acid here. And it looks like nothing happened, basically.
So, no reaction yet?
No, there is a reaction. There's a little bit of heat. And would I notice any smell? I definitely can feel the heat. But that could be heat. Sulfuric acid in water produces heat. So that I should be able to smell what? Vinegar. Acetic acid.
So it is a CCS?
It's a CCS. I don't really smell much of anything. It's so dilute, yeah. But definitely, I'll let you know, a reaction did happen. And our prediction is correct. There are other ways to detect if a reaction occurred or not, but you know, visually I can't tell. Looks like no reaction. And smell, same. All right, what about ammonium acetate plus sodium hydroxide? What forms there? Uh-huh.
What did you just mix? That was ammonium acetate and what?
Ammonium acetate and sulfuric acid. Number 8 or number 9. We're on number 10 now. Ammonium acetate and sodium hydroxide. What do you predict will form?
Ammonium hydroxide, sodium acetate.
Yeah, ammonium hydroxide. Ammonium hydroxide is unstable and it will decompose into
NH.
ammonia and water. So I'm going to take my ammonium acetate and sodium hydroxide, and I should be able to smell what? Not vinegar. I should be able to smell ammonia. This wasn't concentrated enough. It's too dilute, or my sense of smell is bad.
It was burned when you used the hydrochloric.
Yeah, probably the hydrochloric acid. I can't smell anything.
Neither.
And the color changed, but that could be due to other things. But it's correct. We're going to form ammonia. Ammonia, water, and
Sodium acetate.
sodium acetate. Sodium acetate you can't smell anyway. But a reaction definitely happened. There's a driving force for this. The driving force is gas formation, ammonia, or stronger to weaker. Ammonium acetate plus ammonia. Do you want
Is it strong based?
stronger base to weaker base? Or, well, maybe we'll take a look at that one in more detail. This was number 10, is that right?
Yes.
Okay, number 10 is ammonium acetate and sulfuric acid. Was that right? Sodium hydroxide. Then number 9. Yeah, number 9, sorry. Number 9 was ammonium acetate and sulfuric acid. Was that the one that was the question, or number 10?
Number 10.
Number 10? No, well, we could do both. And so this is going to form ammonium sulfate, which the formula would be NH42SO4. This is aqueous, and acetic acid. And so I was trying to smell the vinegar here, because there is a driving force. We're going from a stronger acid, sulfuric, to weaker acid. There's no precipitate in this case. And then to balance this, we'll need 2 ammonium acetates and 2 acetic acids. This would be the CE. The IE, we'd split this apart. Actually, let's do the IE, just to do it one more time. Ammonium salts are soluble. That's going to form 2 ammoniums and 2 acetates. How do we split up H2SO4? Yeah, H plus is a strong acid, and it should ionize into H plus and HSO4 minus. And so we're going to form H plus and bisulfate ion. Ammonium sulfate, that's a soluble salt, so we're going to get 2 ammoniums and a sulfate. And acetic acid is weak acid, so that just stays together. Like that. Okay, what are the spectators? Ammonium is spectator, yes. And that looks like it. And so the NIE is going to be 2 acetates plus H plus HSO4 minus. Acetate is plenty strong enough to take this H+, and it's plenty strong enough to take the H+ off by sulfate. And so it'll take both of these hydrogens. And in that process, it's going to form sulfate. Sulfate is completely stripped of its hydrogen. The first hydrogen comes off from water. Water is plenty strong enough to strip off the first hydrogen. And so acetate's going to take that. And the second one will be taken by the acetate. So we got acetic acid. This would be it. Ammonium acetate is kind of interesting because ammonium is an acid, acetate is a base. So ammonium acetate reacts both with acids and with bases. And so the next reaction we're doing, which is number 10, is taking ammonium acetate and this time reacting it with a base, sodium hydroxide. And what are we going to form here? Ammonium hydroxide. But the situation with ammonium hydroxide is it's unstable and decomposes into NH3 and H2O liquid. I'd like to capture the ammonium hydroxide and sell it because it's rare, but I can't. You're not going to be successful. It's going to fall downhill and form this. Unless at high concentration, you could be successful. You know. But these are the major species, and sodium acetate. Sodium acetate is just aqueous salt. It's going to just stay dissolved in water. And so the IE for this, might as well do that, is ammonium acetate, soluble salt, it's going to dissociate. Sodium hydroxide is a soluble salt, it dissociates. Ammonia, leave alone. Water, we leave alone. Sodium acetate, we dissociate. Then the NIE will get rid of the spectators, which will be acetate and sodium. And so we have ammonium plus hydroxide yields ammonia plus water. The ammonia could be aqueous or gas. It's very soluble, so the other way I might be able to detect it is by heating it. But I don't want to heat it, because it takes time. But if I gently heat this, then I might be able to smell the ammonia. The same thing earlier. If I gently heated the previous one, we might have been able to smell the acetic acid. Just heating it gently, and then we could tell that a reaction actually did take place. Sulfuric acid plus sodium hydroxide, what does that yield? Oh, sulfuric acid plus sodium carbonate. What do you think is going to happen there?
Carbonate plus sodium sulfate.
Carbonic acid, which is going to bubble. So I expect to form lots of bubbles. Sulfuric acid plus sodium hydroxide is going to yield sodium sulfate and water. So in theory, you could drink it, but I'm not. Yeah, the product. Sulfuric acid plus ammonia. Sulfuric acid plus ammonia, we have two ways of doing that. So we're kind of just going to skip, or unless, do you want to see 12, 13, and 14? We'll just do that really quick. So sodium carbonate plus sulfuric acid. Two CCSs, what am I going to get? I'm going to get a CCG. Do you know what CCG stands for?
Clear colorless class.
Clear colorless.
Colorless gas.
Whoops. That was too much. unfortunately. All right. That was a bit too much effervescence, and then it shot out the top, but it's all right. Okay, next, what do we have? We had sulfuric acid plus sodium hydroxide. So I'm going to do that next here. Sodium hydroxide. Wow, do you see that?
No, those are reactions.
There's got to be some stuff in there. I have a waste beaker in here. Let me try one more time. Do you see the precipitate at the bottom of the sodium hydroxide? You know what that is? It's sodium carbonate. Hydroxide's like CO2, so if you exhale on this, it eventually will form precipitates CO2. I'll show that sometime. Plus sulfuric acid. What's going to happen? We're going to form what? Sulfuric acid plus sodium hydroxide forms
Sodium sulfate plus water.
sodium sulfate and water. Sodium sulfate, all sodium sulfate are soluble. Actually, all sodium salts are soluble. Oh, I'm getting bubbles.
Effervescence.
This is not effervescence. You know what these bubbles are? This is getting very hot.
Water evaporation.
It's not water evaporation. Initially, it's not boiling. If it was boiling, I'd say this bubbles of gaseous water, steam. It's getting hot, and the first thing that happens is air, dissolved air, starts to bubble out of water. And so hot water, air is not very soluble. Cold water, air is more soluble. And so this is just air. You see the bubbles come out. It's just air. But it's not boiling. It could be boiling. If I use concentrated sulfuric acid, it would be boiling right now. It's like when you heat up a pot of water. Initially, you'll see some bubbles form on the inside surface. That's just dissolved air coming out, nitrogen and oxygen primarily. Okay, what's next? Sulfuric acid and ammonia. What do you expect to form?
Nitrogen sulfate water.
Nitrogen
Sulfate nitric gas.
Not nitrogen sulfate. Okay, there are two ways of handling this. Option one, aqueous ammonia and metathesis reactions. You treat it as ammonium hydroxide. And so if we did sulfuric acid and ammonium hydroxide, we'd form ammonium sulfate and water. Option two, we do this using Bronsted acid base. If we do this using Bronsted acid base, so we have H2SO4 plus ammonia. Bronsted acid base is a proton transfer, so we transfer a proton from the acid to the base. And so if we transfer one proton, we'll be left with HSO4 minus and ammonium. So we end up with ammonium bisulfate. But bisulfate is plenty strong enough to react with ammonia again. And so ammonia can pluck this remaining proton. Water can't, but ammonia can. And so if ammonia plucks that remaining proton off, then we form sulfate and ammonium. And so overall, if I add these two together, we're going to have H2SO4 plus 2 ammonia yields ammonium sulfate, NH4, 2SO4. This would be the CE, and then I could do the IE and the NIE, basically. And so this is combining these two equations to equal this. This is the net equation here. Alternatively, we could use the metathesis, because we know aqueous ammonia forms a little bit of ammonium hydroxide. And so this is Bronsted. And so I'll take my sulfuric acid and then add aqueous ammonia, NH3 plus water, which forms a little bit of ammonium hydroxide. And so I'll put that in quotation marks here. And then what that's going to form is we go completely. And so we'll get ammonium sulfate, complete reaction, and then 2 waters. Like this. And then to balance this out, I need 2 ammonium hydroxides, which means I need 2 ammonias and 2 waters. And then I look, the 2 waters cancel. And then what I end up with is the same equation as I started off with over there. And so these are 2 ways of handling it. The number 14. What equations did we not do? The CE, the IE, and the NIE. What numbers? 11, 12, 13. Can you do those? Why don't you do those now? 11, 12, 13, and then you can compare them with other people in class. But I want to see the CE, the IE, and the NIE. If you need help, let me know. I'll try to help you. And then that's basically it for the report for this experiment. So complete those equations and then just turn in your observations for this.
Which one of these bubbled over?
The
Is it number 12?
number 12. Number 12 bubbled over, and that's what I'm cleaning up right now.
Yeah, okay.
I'm cleaning up the mess from number 12.
Yeah, I wrote that down for that one, but I wasn't sure.
Mhm.
All right, thank you.
For number 14, for the extra numbers, I just want to make sure. Number 16 is 1, 2, nitric acid.
Number 16. What did you guys have for number 16? I didn't write it down. No reaction, and that was a reaction between what and what? Nitric acid and acetic acid? Yeah. Nitric acid and acetic acid. So, what you can do is, do you have the app Genius Scan or something?
You can use an Apple phone.
Yeah, you could use an app or whatever, and then convert it to PDF. And then what I'm going to do is I'm going to have on Canvas a link to upload your observations. Just upload them. They don't have to be neat, you know. When you take observations like this in lab, they can be a mess. And so this is just, I want to just see your observations for this.
So you don't want the reactions.
Oh no, I want the reactions. You know, all the observations were the reactions and your observations of what happened, precipitation or whatever else, and the reactions. But I don't want the report sheet. In other words.
For the sulfuric acid and ammonia.
Yeah, the CCS. I mean, really didn't see much change. Yeah, nothing happened. Sulfuric acid with ammonia? Yeah. Yeah, I did this one. I think I did this, didn't I? Or did I miss that one? No, I didn't. Okay, we just did it. Sulfuric acid and ammonia. So I have the ammonia here, and then I'll add the sulfuric acid to that. And it looks like nothing happened. There is a little bit of heat, but that heat, remember sulfuric acid makes heat whenever it comes into contact with water.
For the lab, I realized that I made a mistake and I just, like, one digit of the molar mass of oxalic acid dihydrate was, like, off. So could I just fix that and then I can bring it during, like, office hours?
Yeah, that's fine.
Okay.
You could bring it later, or actually only one person turned it in. You can just turn it in next time. Which would be Monday. Just turn it in on Monday. You could turn in your report on Monday. A lot of people forgot to turn it in, it looks like.
Put the report onto the paper.
No, the report for experiment 14. If you want to turn it in, you can turn it in there. The report for this one won't be due until Wednesday next week. So Teresa, there was actually a reaction there, but it's hard to see. Heat, yeah, that was about it.
Can I turn in like this staking?